One of Computer Science 50. So we have a few goals this week. Among them are to, one, set the stage for what we're going to be doing throughout the rest of the semester, focusing on programming and problem solving. What we'll do today is set the context for that, looking at some of the FAS computer systems, Linux, and the like, and we'll also dive into our first C programs. More importantly, what we're going to do this week is introduce some of the basic building blocks, much like we did last week with Scratch, but this week with C, so that come next Monday, we're going to start diving in already to some of the more sophisticated capabilities of C and languages like it, looking at the first of some so-called data structures like arrays, and then moving, as you've seen in the syllabus, towards some of our more interesting problem sets. Among the first will be one on cryptography in just a couple of weeks to come. So a couple of announcements. One, a couple of tweaks have been made to office hours for this coming week, including those for today. So do take a look at the website before you go anywhere. Be sure to section online between tomorrow morning and Friday evening. And then also there's the Engineering Society's dinner for freshmen predominantly in Annenberg tomorrow and Wednesday. Take a look in a couple hours on CS50's website for the time and place exactly. Any questions before we forge ahead? Anything at all? All right, so let's begin, shall we, with a pop quiz of sorts. It's one of those trick pop quizzes where it's not actually a pop quiz, but 8 of you will be involved. So let's raise the bar a bit, and I need 8 of you to come on down here and stand awkwardly in front of your classmates. The upside of coming down now among the 8 will be that you are not among those quizzed. All you have to do is stand here, perhaps raise your hand, but it is a non-speaking role. So I see 2 here, 3, 4, that worked, 5, 6, 7, and 8. Come on down. So if I vaguely pointed to you, come on down. And if there's too many of you, we'll just send some away. Notice that quite coincidentally, we've selected a byte's worth of volunteers. What I need you guys to do is line up here. And over here, you are henceforth going to be the 128th place. Yes. You are the 64's place, 32's place. You'll be the 16th place, the 8th place, and the 4's place, and the 2's place, and the 1's place. So we've got a little binary quiz for you all. And if you guys want to kind of make somewhat of an arc so that as many people as possible can see, what we're going to do is quiz you, the audience, on a bit of binary and see then how this ties into this week's discussion. So on the backs of these pieces of paper, each of these 8 individuals has instructions to them. And we're going to have 3 rounds of this quiz. And on the first round, some number of these guys is going to raise their hand. And if they're raising their hand, that means they represent a 1. If instead they're just standing there awkwardly, they represent a 0. The task at hand for you all then is to, 1, tell us what number they're representing, and then 2, what letter in the ASCII coding scheme they are representing. So without further ado, round 1, if you could all raise or not raise your hand based on your instructions. So I see 2 hands up. So again, the question for the audience is, what number are they representing? OK, so 66, quick recall, what letter therefore are they representing? All right, so capital B. And for those of you who might not be following along quite as quickly, there's your little cheat sheet. All right, so we have number 66, otherwise known as the letter B. Round 2, raise or don't raise your hands based on your instructions. So I see 5 hands up total. Yes? All right, what number are they representing? All right, so all right, you sound a little aggravated. We'll move more quickly. All right, so what letter is that? You know it already? Oh, so we have B, O, and finally round 3, if you would. Boy, no. What number and letter is this? Shout it out when you know the number. All right, 87. And what letter? W, which spells bow. So thank you very much to our volunteers. You can take your bow. Yes, we're going to do this? All right. Congratulations. Keep your papers as souvenirs. Oh, and you all get, if you don't mind, one of these little legal forms, if you don't mind passing these out. Just each give us a signature on those. Okay, so what was the point of this? Well, one, beyond just reinforcing some of the material we did look at last week in that introduction to binary, this stuff's going to come back to haunt, or at least to revisit us this coming week and in the weeks to come as we begin to look at exactly how you represent things like bytes inside of a computer, how you represent numbers, both small, relatively small numbers with just 8 bits and much larger numbers, say, with 32. So just to get some of the basic building blocks out of the way, and just to be clear, if you have an 8-bit value, as we did here up front, how many different possible numbers can you represent? All right, so 256. So if you have 8 bits at your disposal, each of those bits can be a 0 or 1. That is 2 possible values. That's like 2 possibilities times 2 possibilities times 2 possibilities, dot, 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 which is effectively 2 to the 8th, which is 256 different values. So let's scale up. Suppose that we don't just have 8 bits at our disposal, but we actually want a bigger range of numbers, and so we're willing to spend more hardware. We're willing to spend more bits. If I use 16 bits, how many different values can I represent? So it's like 65,536 to be exact. And if you can remember that number in 256 this semester, you're in pretty good shape. After this, most computer scientists, I think, start waving their hands at the totals. Because if we move upwards to 24-bit values, that is, we use 24 bits to represent some number, how many different possible numbers can we represent? 16.7 million. So yeah, so 16.7 million, give or take. And finally, what you usually see being used by many computers today are 32-bit values. And a 2 to the 32 is roughly, so 4 billion is sufficient for our purposes. And nowadays, you might hear about 64-bit computers. And 64-bit computing, well, perhaps suffice it for now to say that that's much bigger, right? So you're multiplying these two numbers together, so much, much bigger. The point, though, is that these are the same building blocks that we use to represent numbers from, say, 0 to 255 are going to be the same basics that we use to represent numbers from, say, 0 to 4 billion. But thus far, we've been focusing, say, only on positive numbers. So thus far, we've said that, say, the number 3 might be represented as 0011. Okay, so that's the decimal number we know as 3. But we've not said anything about how we might want to represent -3. So what might be an approach to representing -3 instead of just +3? All you have in this world are bits. So even if you have no idea what the right answer is, what's a possible answer to this problem? All right, so we can do something similar to what we do in normal life, which is sometimes for clarity we say that something's +3, and then of course we say something is -3, thereby using another symbol to the left of the digits. Why don't we borrow that same idea? So what in binary might be +3 as such, well, why don't we just steal this leftmost bit and just henceforth assume that, you know what, if that thing is not a 0 but a 1, just assume that this number is not +3, but -3. It's a useful trick, but at what cost does this trick come? So I heard a lot of murmurings. I'm going to assume that among the answers just murmured were, well, you're sacrificing the bit, which is doing what to the total numbers of values that you can represent? It's halving it, right? If each of these gives us twice as many possible values, well, if you steal just one of those bits, you're halving your possible range. Now, that might be a reasonable price to pay. It might not be. What we'll see over the weeks to come is that when you want to use numbers in your own programs, you can actually specify if the computer should treat those bits that you're using in memory as either signed, so to speak, or unsigned. And if they're unsigned, that means you get 0 to the biggest possible value. But if it's signed, of course, you sort of shift everything down. So you get a lot of negative numbers and a lot of positive numbers. A total number is the same, but you don't get as high up, say, in the positive range. So this approach here, this very simple approach of just flipping the leftmost bit, the highest ordered bit, so to speak, is called the Signmagnitude approach. The Signmagnitude approach. And what it's called isn't so important, but it's pretty much the simplest way we might do this. Another way that computers represent negative numbers, which is common among older systems in particular, is to take the positive version of the number and then just flip the bits. So it turns out that just by doing that simple trick and representing positive numbers by inverting their bits, one, you have this side effect that the leftmost bit also sort of by chance happens to signify that the number is negative, so that can be useful. But it also turns out if you represent negative numbers like this by flipping the positive equivalence bits, you can start adding bits together, and the math just kind of works out relatively easily. Well, what do I mean by that? Well, let's take a simple example just in the world of positive numbers. If we want to do the binary equivalent of 4 plus 3, well, quick, what's 4 in binary? All right, so 0, 0, 0, 1, 0, 0. And again, I'm for just habit in writing these things in groups of 4. I don't have to include that leading 0. I could include 4 more. I could include 28 more. Any number that I want. Leading zeros are largely irrelevant. 3, by contrast, is what? 0, 0, 1, 1. Well, just like grade school math, what's 4 plus 3 in binary? Well, 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 0 is 1. And this, of course, is 7. So math with binary works exactly the same as you're used to. What about for negative numbers? Well, essentially the same idea applies, whereby if you use what's called the ones complement representation for negative numbers, whereas this was the sign magnitude. And again, the names aren't so important, but just the fact that they're different is. So if you use the ones complement, essentially using the right kind of hardware, you can similarly line up a positive number with, say, a negative number, do that math, and you have to do a little bit of trickery to make sure that the math works out correctly. It involves carrying. If you have a carry, pulling it back in to the start of the number, but we'll wave our hands at that today. But this approach of ones complement isn't so in use today. Rather, there's the approach we will spend just a moment more on, which is the twos complement. And this is relevant because it will come up later in the semester. So suppose that we instead don't want to add 4 plus 3, but 4 plus minus 3, aka 4 minus 3. Well, we can use, of course, the representation we're used to for the positive number. If we instead want to use the twos complement value of 3, to get the negative, what you do quite simply is this. You take the positive number, you flip the bits, but this time you add 1. All right, so let's take that example. So positive 3 again is 0, 0, 1, 1. So if we flip those bits, that gives us temporarily 1, 1, 0, 0. Add 1 to that, and you have 1, 1, 0, 1. So this value here, in contrast to this one now, and this one, is the twos complement representation of negative, in this case, 3. So this is twos complement. And I promise there's no more complements after this. So twos complement. So we're going to line this up, 1, 1, 0, 1, and add these together. Literally add them together. So what do we now get? Well, we have 4 plus what appears to be negative 3. So 0 plus 1, 0, 0. 1 plus 1. 0, but carry the 1. That's 1, and now let's just assume that that gets thrown away. We won't dwell on the kinds of carrying details, but now we appear to have what final result? Just 1, which turns out is exactly the answer for 4 minus 3. So we end on this note with twos complement because 1, it's what's largely in use by most hardware platforms today. But 2, it also tends to be the simplest mathematically. Because of this act of flipping bits and adding 1 to come up with a negative value, literally addition is identical to subtraction because you just line the values up and add them together. And that's useful largely for performance reasons and for simplicity, reasons of simplicity. It's a lot easier to implement hardware that only has to know how to do one type of mathematics and not have to worry about, for instance, carrying bits when they overflow and those kinds of minutia. Yeah? So in this case, so essentially the heuristic you use when doing this is if certain types of carries, which this was, get thrown away. But there are certain types of carries that essentially you can't throw away because what it means is that the number the answer is too big for the total number of bits you have. But again, come on up afterward and we can do a more technical example than that. But for now, let's just emphasize what the representation is. Yeah?
For example, you have that negative number. How do you differentiate? How do you dispatch negative number instead of just calculating it as a normal?
So for instance, this number here?
Yeah. Why isn't that?
So good question. So when the computer sees somewhere in its memory a 1, 1, 0, 1, and it's only using 4 bits, say, to represent numbers, how does the computer know that this is a negative value versus a positive one? So it's 1. This is, again, a sort of hint. Because of the way 2's complement works, you can, in fact, look at the highest ordered bit, and you can infer that that is, in fact, a negative value. And so thus, if the computer wanted to display this thing, I mean, in theory, it could flip the bits and add 1 and then display what the positive number is with a minus sign in front of it. But again, for now, we don't want to dwell so much on the hardware details, but the leftmost bit does tell you whether it's negative or positive because of 2's complement. How do you take a negative value in 2's complement back to its positive equivalent? Again, the nice thing is about this representation, flip the bits, add 1. So it doesn't matter if you're going negative to positive to negative. It's always as simple as flipping the bits and adding 1. Yeah? Okay, so a -3 and 13. So that's a good question. So this, again, is the 1's column, 2's, 4's, 8's. So this looks like 8 plus 4 is 12, plus 1 is 13. It's context sensitive. If you're assuming that your numbers are only represented with 4 bits, then this represents the -3. Because the computer knows that the leftmost bit essentially is indicating sign. If instead we were in a different context, and instead the computer were using 8 bits, and I don't want to make this too messy, but if instead the context simply were that the hardware that the computer is using doesn't just use 4 bits, but uses 8 bits to represent everything, that then makes it clear that this is in fact positive 13 and not -3. So again, it's context sensitive. It depends on the assumptions the computer's making. And actually, either today or on Wednesday, we'll see exactly how you, the programmer, specify just how many bits should be used for values, thus giving hints to the computer as to how it should interpret those bits. Yep?
Is it just coincidence that this complement in this case is one complement of Signmagnitude, or are you always just combining it?
Is it just a coincidence? So all of these different representations are related, and this idea of flipping bits and adding 1 is sort of the layman's heuristic for coming up with the values. It actually, these representations, 1's and 2's complements in particular, actually have to do with the fact that you're subtracting the value from a power of 2, which is only to say these things are related, but let me wave my hand at that for now. Other questions? Yeah. Good question. Is it possible to represent 13 with just 4 bits? So not if you want to support negative numbers. Because if you think about it, if you have only 4 bits, but you want those bits to be interpreted as signed, so to speak, capable of representing negative and positive numbers, effectively we're using that leftmost bit, in this case sort of as a side effect, as an indicator of whether the number's positive or negative, which means you have how many bits left for actual numbers. You have just 3. And if you have only 3 bits, how many different numbers can you represent? 8. So in fact, no. With just 4 bits, if you want to support positive and negative numbers, you can't express the value negative or positive 13 with those bits. Good question. Yeah?
How do you represent -5?
So how do you represent -5 with 4 bits? All right. So let's consider this. So this is going to be what value? So this is positive 5. Agreed? All right, so what using 2's complement would be -5? All right, so you want to go for 6? All right. So 0, 1, 1, 0 is positive 6? You want to keep going? Yes? Keep going. Or you're OK. All right. So what do? We flip the bits. So we get what? 1, 0, 0, 1. Add 1, 1 from the side. There's murmuring, but what?
Originally, where you flipped it horizontally versus flipping each individually, it's the same thing.
Oh, did I do something wrong early on?
So I thought you were just reversing it, like left to right, going right to left, but toggling the.
OK. OK, so to be clear, OK, good. OK, so fair point. So when I say flip the bits, I don't mean take the mirror image of what the number looks like. OK, common source of confusion. Flipping bits means toggling them. 0 becomes 1, 1 becomes 0. OK. All right. So now the past 10 minutes are more clear? Okay, so I didn't realize, I'm sorry, that flipping is a term I've taken for granted over the past few years. So flipping bits means to make a 0 a 1 and a 1 a 0. So it's sort of like flipping them in this sense. All right, one more question.
So, back to the previous question, if you can't represent 13 with 4 bits, then why is the 2's complement more efficient than the sign magnitude?
So, okay, if you can't represent the number 13 with 2's complement, why is sign magnitude more efficient? It's not more efficient in the sense that you can represent more numbers. It's more efficient in terms of how it can be implemented in hardware. It's just easier for a computer to essentially treat numbers, positive and negative, using this 2's complement representation, because the same circuitry can be used for both for both addition and for subtraction. The fact that we're getting hung up on this idea of just using 4 bits, which is kind of funny because never again will we ever talk about using just 4 bits in this class. The fact that you can't represent 13 with just 4 bits is just a reality of what you can do with bits and how the base 2 system works. The solution to that problem is just use more bits. It has nothing to do really with the choice of representation. Okay, so let us forge ahead, if we may. Okay, and today's takeaway will be, if you learn nothing else, you've learned what flipping bits actually means. Okay, so last week we focused on this language called Scratch, and we've already seen that a number of you have begun uploading your projects to MIT's website, which is fantastic. So those of you who are curious to see what your classmates have submitted, by all means follow that link toward week's end and see what kinds of things folks came up with. So we begin today our transition from Scratch to C, but one of the points will be that the concepts, the underlying fundamentals, are pretty much exactly the same as those that we'll use in this more traditional world of C. But the types of languages that we've been looking at are different. That is to say, Scratch is sort of fundamentally a different type of language in the world of computer science from that of C. And it's distinct, in fact, from things like PHP and Perl and Python and other similar languages. So what we wanted to begin today with is a quick categorization of some of these different types of languages. Well, let's begin with a scenario you're familiar with. When you wrote, what did it mean to write a program in Scratch? Drag and drop. Okay, so you dragged and dropped some puzzle pieces, effectively creating what we've called source code. Then you clicked play, and then what happened? So the animation or whatnot progressed. Well, it turns out that when you write a Scratch program, and this was one of those .sb files, essentially you're not running it on your Mac, and you're not running it on your PC or even your Linux computer directly. Rather, those programs are being run on what's called a virtual machine. And this is a term that you might have heard increasingly even in the media these days, as companies like VMware, a spin-off of EMC, have recently gone public. So this term VM, virtual machine, is increasingly commonly cited because of the advantages that it purports to offer. Well, how does this scenario work? Well, essentially, when you run a Scratch program, the bits that comprise it aren't being fed directly to your computer's CPU, but rather they're being fed to this virtual machine. The virtual machine is just a piece of software. The software that understands what the language known as Scratch knows how to interpret, rather, the language known as Scratch. It's underneath this so-called virtual machine that your computer's CPU is. So in other words, what was the first thing you had to do in order to begin working with Scratch? I mean, you had to download the installer. You had to download that program. Well, what really were you downloading? Well, besides the sort of software development environment you were downloading, the thing you interacted with, really what you were downloading was a piece of software known as a virtual machine. Scratch actually happens to be implemented underneath the hood in a language called Smalltalk, or Smalltalk 80, or more specifically something called Squeak, for those of you familiar with various types of languages. So essentially, when you run a Scratch program, it's not being executed directly by your computer in the spirit we described last week, but rather by this virtual machine, which is just a piece of software running on top of your computer. The advantage of this is that it makes it, among other things, easier for MIT to roll out support for Scratch on multiple platforms. So did any of you note that the programs, when you pull up MIT's website and just have the ability to play classmates' projects, they sort of look different than they do when you're actually using them on the client-side software that you downloaded. For instance, the text looks a little different. I even mentioned that Oscar time behaves differently in the web-based version versus the client-side version. Well, the reason is that the web-based plugin is just virtual machine software that was written separately from the version that you downloaded to, say, your Mac or your PC. So it just happens to have some differences in it that it still understands the language known as Scratch. It still understands Smalltalk, the underlying language being used there, but it has implemented it somewhat differently. Well, those of you who have come here out of computer science, AP Computer Science, probably have entered knowing the language Java. Java works exactly in the same way. When you write a Java program, you can run it on a Mac, on a PC, on a Unix computer. It doesn't matter what type of computer you run it on, because Java 2 is sort of platform independent. It's portable. These are sort of synonymous terms. What that means is when you ran a Java program in AP Computer Science, those of you who did, what was the command you typed to run a Java program? Java space, hello, right? Whatever the class name was. Well, what were you doing? What you were doing was running the software called Java and then feeding it the code that you had compiled, the so-called bytecodes, and then the virtual machine was responsible for essentially communicating with the CPU and getting your program ultimately to execute. Now contrast this with the world you're all familiar with. When you sit down at your Mac or your PC and you want to run AOL Instant Messenger, well, what do you do to run that piece of software? You double-click it, quite simply. Well, what does that do? When you double-click that icon, the bits that comprise AOL Instant Messenger are literally being fed directly to your computer's CPU. So when you click aim.exe, I mean, the convention of naming Windows programs .exe means they were specifically made for certain types of CPUs, namely Intel CPUs predominantly, and the fact that, and for Windows in turn. By contrast with Mac OS, if you double-click a Mac OS icon, it too runs the program directly on the PowerPC CPU or on the nowadays Intel CPU, but it runs directly in this sense. Well, how can we make this more real? Well, why is it that you can't run, say, AOL Instant Messenger for the PC on your friend's Macintosh? Or equivalently, why can't you say your friend who owns maybe Microsoft Office for their PC, why can't you take their installer CD, take it over to your Mac, put it in, install it, and run it on your Mac? Sorry? Yes, it's illegal. And product keys. You need a registration code is what you were really getting at. But that's actually not even the technical explanation. That's sort of a commercial explanation for why you can't do that. In more real terms, when you write a computer program traditionally, you're again writing this thing known as source code. And we'll see some source code in the language known as C today. You've seen source code already in the form of Scratch in terms of those puzzle pieces that you dragged and dropped. But traditionally, when you create a program, you run that program, you run your source code through a special program called a compiler. And what the compiler outputs is what we'll generally call in this course object code. So if you are someone working at Microsoft and you've just created the latest Microsoft application, obviously for PCs running Windows, well, you take your source code, which might just be one big text file. It might be these days dozens of, hundreds of, thousands of separate files, but they all get run through a special program called a compiler. If you've ever heard of Visual Studio or Visual C++, those kinds of things, those are just compilers for the Windows operating system. Well, you run your source code through a compiler, and what you get out is something like something.exe. The bits inside of something.exe are laid out in patterns that only Intel CPUs can understand. They are not understood in the same way as, say, a PowerPC Macintosh's CPU would understand. So the idea is that ultimately, it's not just the programs per se, but it's these compilers that are specific to the hardware and to the operating system that you're creating your program for. So in this course, when we focus on writing programs in C, we're going to be doing it predominantly within a Linux environment. And you're going to be using a compiler that's called GCC. And this is sort of a Unix equivalent of Visual Studio. When you create these programs, they're only going to run in a Linux computer with an Intel x86 processor. However, you could take your same source code, and some of you typically do this each year. You can take your same source code, copy it to your own Mac or PC, run it through your own compiler, and you could certainly run all of CS50's programs this year on your own computer. You might have to jump through some hoops to make that happen, but at the end of the day, it is possible. But the takeaway for now is that typically when you compile software from source code into object code, aka .exe files, they are platform, that is operating system, and or hardware specific. Yeah?
Most of the Mac programs and the PC programs, are they written in CC?
Good question. So most Macs and PC programs today, actually, to date, they do still tend to be written in C, C++, C#. One of the reasons you actually see so many security holes in some of today's most popular software is because they are written in C and C++ in particular. Well, later in the semester, actually, we'll focus on some of the security implications of languages like C and C++. But the fact of the matter is, and we'll come back to this today, just for the same reason that C and C++ give you more power, more control over the hardware, they also tend to put you at greater risk of making mistakes, and making mistakes that can compromise the security of your system. So later in the course, we'll actually spend a lecture at least on secure coding, or really insecure coding. Other questions? OK, so again, this categorization. So Scratch and Java fall into this category of languages that run atop virtual machines. And they're compiled into, again, these things called bytecodes. So the languages we're going to be focusing on in this course are things like C. But also in the same category as C are things like C++. And things like this get compiled into object code. Object code. These are what are known as compiled languages. And this is in contrast with another set of languages like Perl and PHP and Python and a whole bunch of other programs that get not compiled per se, but interpreted. So the two broad categories of languages that we'll discuss in this course, focusing more so on these, are ones that are compiled and those that are interpreted. And we'll see with a couple of demonstrations in just a bit what that means in real terms, either today or on Wednesday. All right, so we promised last week that this is the kind of stuff you're going to start writing. At top left here is a program in C. That big red arrow there is simply meant to represent the process of running your so-called source code at top left through a special program called a compiler. And a compiler, again, outputs this stuff called object code, or .exe files in the world of Windows, that ultimately, as you know now, are going to look just like zeros and ones. So how are you going to start doing this sort of thing in this course? Well, again, in this beautiful utopia here known as the Science Center, there are a whole bunch of computer systems running Linux. Those systems are collectively referred to as nice.fas.harvard.edu. In other words, you in this course are going to be connecting to this cluster of computers that just boasts this name, NICE, which is the new instructional computing environment, to contrast it with ice.harvard.edu. The irony is that these new computers, NICE, have now been around almost as long as I've been here. So 8+ years have they been new. And you'll also see, if you ever look underneath the hood, those of you with more arcane Unix skills, the naming scheme behind these machines is an absolute mess. But that's a bit of an aside. We will just call this the NICE cluster, nice.fas. So it's a bunch of Linux computers running behind a locked door in the basement of the Science Center. You presumably will never have physical access to the machines. Odds are they don't even have monitors or keyboards, because the purpose of these machines is to allow people on campus to connect to them remotely. So this thing called an FAS account, your username at fas.harvard.edu, is precisely the username and password that you'll use to connect remotely to these computers using two languages, or really protocols, that we'll introduce as SSH and SFTP. So what does that mean? Well, this is the kind of screen that you're going to get to know and love in this course. This is what's known as an SSH client. Pictured here is a program called Secure CRT, and it happens to be the Windows version of this software. If you have Mac OS, you actually have this software built into your computer called Terminal. It's under Applications, Utilities, and there's a program called Terminal, and your world will look a little more like this. The content, though, will be the same. Yep? If you accidentally deleted Terminal, I'm guessing you didn't actually delete it, but maybe you deleted the shortcut to it that's in maybe your little system tray thing. I'm sure there's a way to fix this. Let me invite you to our office hour someday this week. So this is what the interface is going to look like, and what might jump out at you immediately is that this does not look all that glamorous. In fact, it is purely text-based. Those of you who have used or remember DOS was what's known as a command line interface. Well, so is Linux, or really Unix, a command line interface, even though you do have things these days like windows and icons and menus. And if you sit down at the Linux computers in the Science Center, you'll see that kind of environment. But what do we mean by saying that you're going to be using this cluster of computers remotely? Well, essentially, the process that you'll quickly become accustomed to in this class, and in others perhaps, is as follows. I, on my computer, have downloaded from the course's website this program called Secure CRT. You don't have to worry so much about what I'm about to show you specifically, because there's a handout on the course's website per problem set 0's directions. I've installed it, I've configured it, and now what I'm going to go ahead and do is go to File, Connect, and now you see this default list of all of these different computers on campus. Here's NICE. Here's one called wally.eeks.harvard.edu. Here's one at HCS. But the one we want is called nice.fas.harvard.edu. I have parenthetically their lecture because I reconfigured this session, so to speak, to have a much bigger font so that everyone could see it better. So you're going to be prompted whether you're using Mac OS or Windows for your username. The one I'm going to use is called CS50 test, which is a little dummy account we use. Then you're going to be prompted for your password. Go ahead and type that there. Again, this is just your FAS username and password. And voila, you're going to be at that blinking prompt that was promised a moment ago. The very first time you connect to this account, as problem set 0 instructs you, you're going to run CS50 setup by typing that command. And for those of you a little uncomfortable with this world, if you make some syntax errors, for instance, like this, you might very well see command not found. That means it's most likely your error, not actually ours. So do check your commands. Hit enter. And again, you're only going to do this once. The screen is going to tell you, great, go ahead and log out, log back in. What this does for now isn't so terribly important, but know that it configures your account for use in this course, so that essentially we're standardizing what all of your computing environments look like and giving you sort of behind the scenes access to special software we've installed on these computers so that you all have a uniform experience. What we now have here is a blinking prompt of the form username at NICE. Obviously, username will be filled in with whatever yours is. And now I have this ability to do stuff at the command line. All right, that's clearly not a command, but let's give you some of the basics here. And again, these things are, you can jot these down as notes, but there are references available on the course's website. Perhaps the most useful command to know first is in lowercase ls, which stands for list. A list simply lists the files in your current working directory or present working directory. Well, what do I mean by that? Well, the fact that I have just connected to NICE via this SSH program, which just stands for Secure Shell. It means everything you're doing is encrypted between you and the Science Center. What I have at this blinking prompt is what's called my home directory. So on all of those FAS systems, you have what's called a home directory, which is like your own personal storage space. And by default, I think you all have 50 megabytes these days for coursework and other things. It's not terribly much these days in light of Google and such giving you gigabytes of space elsewhere, but Harvard only gives you just 50 megabytes for all your email and storage space. But that's fine largely for our purposes. So what does this mean to have access to your home directory? Well, when you type ls, you're showing the contents of what's in your home directory, in the folder that you own. If I type this command pwd, present working directory, this shows you where you are in the system. So again, because everything is written at the command line, and we can't just go double-clicking through folders, what that output indicates is that I'm in my home directory called CS50 test, which happens to be inside another folder called S, which itself is inside a folder called C, which itself is inside a folder called home, which itself is inside a folder, it seems, called NFS. So memorizing these kinds of things, not all that useful, but what is useful is when you start moving around in your directory. So one of the first things problem set 0 is going to have you do is type mkdir, which if you've never seen it before, take a guess what that means. Make directory. I mean, the reason for these shorthand notations is that back in the day, and even nowadays, it's a lot faster to type ls than list. So the reason that you're missing all these letters sometimes is not so much for clarity's sake, but for efficiency's sake. I'm going to create a directory called CS50 and hit enter. Nothing appears to happen, but now if I type ls, I see that there's a directory in there called CS50. How do I open a folder? Well, you can't double click it. Do bear in mind, and you might fall victim to this, clicking around on this window does nothing. You can highlight, but you can do nothing else with it. So if you see one of your innocent oh, that guy. If you see one of your friends clicking around on the screen and nothing actually happening, like it my way better, then remind them that this is just what's called a command line interface. So if we go ahead and type cd for change directory, and then go ahead and hit enter, notice too that my prompt changes. And this is one of these little niceties that we've configured your accounts with, so that you have a constant reminder of where you are on the FAS system. Always in parentheses will it tell you that you're in your home directory, the shorthand for which is a tilde, / whatever folder you're actually in. If I type ls now, what should I see? Odds are nothing, because all I did was make a directory. It's like on Windows or Mac OS, just right-clicking and saying new folder or some such thing. All right, now I'm going to go ahead and make, for instance, a PS0 directory. This, too, is something problem set 0 has you do. If I type ls now, obviously I'm going to see that directory. If I cd into that, I'm now inside that folder. So now if I type that same command from before, present working directory, the path along which I've traveled is much longer now, because I'm now 2 directories deeper. Okay? Other things that you might want to do is write your homework. Nano is the name of a program that you will be using at least early on in the semester, if you're familiar with no other Linux text editor, to actually write things like source code and answers. Creating and then opening and creating a file at the command line with this program called Nano is as simple as typing nano space file name. And what you get is a screen like this. Those of you who use the email program Pine will actually find Nano almost identical in functionality to Pine. It's just for writing text files, though, not actually sending emails. But if you wanted to say then, this is my questions.txt by David Malin. And then I could proceed to go ahead and answer my answer to ... There's only 4 commands that are particularly useful to know. They're all documented in problem set 0. Control X is the command to save. You're going to get a fairly cryptic message like save modified buffer. That just means do you want to save the file or not. Hit yes. You're going to be reminded what the file name is in case you want to change it. So the analog here is like save as in the Mac OS or Windows world. Hit enter. Done. So assuming I've just actually typed all my answers, if I now type ls, quick sanity check, what should I see? Questions.txt. In fact, I do. If I go ahead and open it again and hit enter, I can then continue editing the file. So this is, think of this as like Notepad for Windows, or TextEdit, I think it's called, in Mac OS. The simplest of text programs. But for us, it's actually going to be useful because it does offer a number of programming-related features. Things are going to become quite colorful soon when we start writing C and not just questions.txt. Things are going to indent nicely for us. So it has a lot of these nice programming-related features that you'll see. Those of you who already know things like VI or Vim or Emacs, by all means, start the course by using those. We'll introduce more sophisticated text editors over time. For now, this is a quick and dirty one that's easy to use and gets the job done. So what else can you do on these systems? Well, here's just a list of some commands. We already looked at a few of these, cd and ls. CP is going to be the copy command that you'll start using. And again, you don't have to memorize these things now. We'll give you examples of them when it becomes relevant. MV is the move command to move a file around or to rename a file. RM is the remove command, which is going to delete a file. And man. Man is perhaps one of the more useful commands. It's shorthand for manual. Anytime you want to look up documentation, somewhat technical documentation on these systems, you're going to type man and then the keyword that you want to look up. But we'll give you examples of that in the future. So some more interesting programs. Those are really just basic commands. You'll see over the next several weeks commands like check in and check out, CI and CO. We're going to give you the means in this course and hopefully the lifelong lesson of constantly backing up your work using what's called version control, so that when you screw up and either break your C code by making some mistake at 1 a.m. and you just can't think straight anymore, you can actually check out, so to speak, an older version of your code, essentially a backup. And we'll show you very nice tricks to automate that process. CS50 submit is the command you're going to run to submit your work. Emacs and VI and Nano are all text editors. Make is a command that you'll use to compile. GCC is another command you'll use to compile. Oh, and then, what is this one doing here? SB. Oh, well, it turns out that damn it. Okay, what a demo. I encourage you all to try SB, which was implemented by a former CS50 student himself. So, how to write a program in C. So we would be remiss if we did not at least show you how to begin writing C programs. So in 3 steps, this is how you write a program in C, really on any environment, but specifically on the nice systems. What I'm going to do is go over to my SSH window, and I'm going to do this in my home directory. I'm going to put this file elsewhere online for you later, and I'm going to write nano hello.c, or rather hello1.c. And the first things I'm going to have to type, and for today, just take for granted that you have to type some of this stuff, even though we won't quite reveal what it's doing. I'm going to type this cryptic thing, include standard.io.h. I'm going to type int main. Then I'm going to type this thing, int argc, char star, argv. OK, but notice how colorful it is, right? Programming's fun already. And now we're just going to do that very simple hello world program. I'm going to type printf, quote, hello world, close quote, semicolon. OK, so this is the syntax that we said initially can be a little easy to trip over, because there's all these minutiae of semicolons, parentheses, keywords that you might not understand yet. For now, that's all I'm going to do. I'm going to hit Control X to save, because again, I'm just in Nano. I'm going to hit Y for yes, Enter to confirm. When I go ahead and type ls now, you see hello1.c. Oh, no, I know. It's instructive example. What I'm going to do now is try to run this program. Unfortunately, it's not as simple as just typing, for instance, hello1.c. This isn't the world of Linux and Mac OS where you can just double click on things. Rather, you have to compile this program. You have to use a compiler. That compiler is called GCC. GCC space file name is as simple as it gets. This is going to create the equivalent of an exe file in the directory. But by default, notice that the file that was created is called a.out, which for historical reasons is assembly.out or assembler.out. But if I want to run this thing now, I can simply type a.out. And finally, we seem to have our first bug, as Thomas preemptively pointed out. What's clearly the problem here, assuming we're being anal about aesthetics? All right, so it'd probably be nice if this thing actually moved to a new line. So let's fix this real quick. So the thing you've seen throughout your examples thus far are, again, these somewhat cryptic things like \n. Well, you can kind of guess that what this is going to do, it's going to create a new line. So if I go ahead and recompile this thing by retyping gcc hello1, and then go ahead and type a.out, now actually I have my very first C program. And let's make it ever so slightly more interesting, because a.out is perhaps the stupidest thing to call your program if you want other people to use it. Let's go ahead and give this an actual name. So the better way of writing a program on these systems is to actually specify the output name that you want to give your thing. So this time I'm going to say gcc-o hello1, and then the name of the file. Hitting enter now creates a file called hello1. The star that you see there just means it's executable. It means you can actually run it and not just look at it. So if I type hello1, now I have my very first program. As will you come Wednesday. See you then.